Today we got to get into power series. We want to use power series as models for some function. This could be a function that we know, or it could be a function that we don't know. We have a description of a function. So a power series is could be used as a sketch of a function that we know nothing of, that we only have a description of, like in a differential equation, for example. We can also use a power series as a model for a function that we know. Like we can create a power series that's a model for cosine x. That's not quite as useful in an age of massive amounts of computing power, but we can also use power series for functions that we know but can't do certain things with, like cosine of x squared. So if we want, say, to construct an antiderivative, and our function does not have a nice antiderivative, then we can create a power series description. Notice that the form of a power series is that of polynomial. It's like a polynomial, but keep going, like an infinite degree polynomial. And we want to know what stuff can we plug into the power series. That's the question for a power series. As far as the parts go, the Cn, we're going to call those the coefficients. I usually refer to A as the center of the series. And X is our input. We have an input, a center, and then we have the coefficients. Notice that the center is the same in all the terms. The center describes the form of the terms. So if we have something like with an x minus 1, then an x minus 2, then an x minus 3, that is not a power series. We have just powers of x minus a, something we can identify as the center of the series. They are being multiplied by these coefficients, and our job is to determine what inputs produce a convergent series. When we substitute a value for x, we get a series. So when we plug stuff into a power series, we end up with a series as an output. So the input is a real number, the output is a series. We input a real number x, the output is a series. We want to know for what values of x do we get a convergent series. The question for us, our job, is to determine what values of x produce a convergent series. Our job is to determine the values of x that produce a convergent series. For some power series, the convergence will depend on the value of x. Do a simpler example. So in this case, our center would be at 0. So in this case, I've set A up equal to be 0. And our coefficients are 1/3 to the n. So this series looks like when n is 0, we get 1. When n is 1, we get x 1/3 x. When n is 2, we get 1/9 x squared. When n is 3, we get 1/27 x cubed, and so on. Looking at these terms, if we think we see exponential factors, x to the n is an exponential factor, 3 to the n is an exponential factor. So we know that a ratio test is a good idea here. Ratio test says absolute convergence if the common rate, or if the rate limit from the ratio test is less than 1. So that'll happen so long as x is less than 3. If x is less than 3, then we have a geometric series with a common ratio less than 1. That'll converge. And if x is greater than 3, then we'll have a divergent series. If x is equal to 3, then we get a divergent series as well, because all the terms will just be 1. So what we want to notice is that sometimes this series converges. So when we plug in a 2, we get 2 to the n over 3 to the n. That's 2/3 to the n. Which is geometric with a common ratio of 2/3. And 2/3 is less than 1. Or 2 to the n over 3 to the n, we can say that the limit from the ratio test is going to be less than 1. So we would say that the power series converges when x equals 2, or the power series converges at 2. We might say when, or we might say at. I will switch back and forth randomly between the two. Sometimes I'll write an open 4, sometimes I'll write a fantastic 4. I never know what I'm going to write. So the power series converges when we plug in 2. With the input 2, the power series converges. But if I plug in something bigger than 3, then the series diverges, or we get a divergent series. If x equals 4,4 to the n over 3 to the n diverges. The limit of the terms goes to infinity, so the limit of the terms is not 0. Also, the limit from the ratio test would be 4/3, which is greater than 1. So we would say that the power series diverges when x equals 4. So we have a very different question running around here. We don't look at a power series and say converges or diverges. It's not a multiple choice problem. It's kind of a multiple choice problem, but it's like an uncountable choice. When you're looking at just a series of constants, it's a multiple choice problem. Diverges, conditionally converges, absolutely converges. When you're looking at a power series, the question is, what values of x, for what values of x does the power series converge? A thing to note, that if x equals 3, then we're looking at 3 to the n over 3 to the n, which is just a sum of a bunch of 1s. Here, the series diverges because the limit of the terms is 1, which is not 0. Note that we cannot use the ratio test here. The limit from the ratio test is 1, which is not helpful. So in this case, the limit from the ratio test is 1. That's not helpful. That doesn't tell us anything. But we would look at the terms and say 1 does not go to 0. So the power series diverges when x equals 3. Oops. So when we're looking at a power series, sometimes it will converge, sometimes it will diverge. We have to know the values of x that will make this happen. What values of x will make the power series converge? What we're looking for, the set of all x for which a power series converges, is called the interval of convergence. Our job is to find the interval of convergence. That is the set of all x for which the power series converges. This contains 2 pieces of information. 1, the convergence part. This is the set of all x for which the power series converges. We care about where the power series converges. Number 2, I have called it the interval of convergence. This is a statement about the form of this set. This set will take the form of an interval. So the set for which a power series converges will take the form of an interval. That's why we call it the interval of convergence. Instead of just like the set of convergence. It may look very inefficient to just poke around different values of x and try to figure out where the power series converges. That's only because it's very inefficient to just poke around different values of x to figure out the interval of convergence. We want a nice, clean way to figure out the interval of convergence. Fortunately, we have one. To find the interval of convergence, use the ratio test. We are going to use the ratio test to find the interval of convergence. This is not actually the entire story, but this is going to be the headline. We're going to use the ratio test find the interval of convergence. We're actually going to use the ratio test to find most of the interval of convergence. Almost all of it. We're going to use the ratio test to find almost all of the interval of convergence. The ratio test is blind at the endpoints of the interval of convergence. The ratio test might not know what's going on at the endpoints. We need to check the endpoints of the interval, if there are any, using something besides the ratio test. The limit from the ratio test will be 1 at the endpoint of the interval of convergence, if there are any. The limit from the ratio test is 1 at the endpoint if there are any endpoints. That's not helpful. The reason the ratio test is so effective at this game is that the ratio test says if this happens, then the series is absolutely convergent. And if this happens, the series is divergent. It has very clear, simple instructions to follow. It does have the one case where it doesn't work. If the limit from the ratio test is equal to 1, then we get nothing, and we have to go do something else. But that only happens at the endpoints if there are any. Let's look at our simplest power series. Remember, we can use different values of x. So when I wrote the series like 5 to the end, that diverges. But if we have something less than 1, then the series converges. If x is equal to 1, then we just get 1s, and we get divergence in this case. Let's do a ratio test. I just set up here to do a ratio test, so let's do a ratio test. The n plus first term is x to the n plus 1, and the nth term is x to the n. So we'll take the limit as n goes to infinity of the absolute value of the n plus first term divided by the nth term x to the n plus 1 over x to the n will just leave behind an x, an absolute value of x. Notice that our limit is as n goes to infinity, but n just dropped out. It's the limit as n goes to infinity, not x. Notice that it's n goes to infinity, and there is no more n in our expression. So as n goes to infinity, this expression that doesn't care about n anymore is just the absolute value of x. This absolute value of x is the limit from the ratio test. This absolute value of x is the limit from the ratio test. The ratio test says if the limit from the ratio test is less than 1, then the series is absolutely convergent. So if this power series converges if the absolute value of x is strictly less than 1. This is almost all of the interval of convergence. In this case, this is all of the interval of convergence. The ratio test does not know what's going on when x is equal to 1 or when x is equal to negative 1. Let's draw a picture of this power series. This interval. The absolute value of x less than 1, if we draw a picture of it on number line, has 0 at the center and a radius of 1. The ratio test has confirmed that anything strictly between -1 and 1 is part of the interval of convergence. Now make the geometric common ratio strictly less than 1. The endpoints -1 and 1, the ratio test does not know what's going on. Those are the endpoints, and we have to check those. We need to check the endpoints outside of the ratio test because the ratio test does not know what's going on there. So if x is equal to 1, the series looks like n goes from 0 to infinity of 1 to the n, which is a bunch of 1s. So the power series diverges at x equals 1. Limit of the terms is not 0. So 1 is not part of the interval of convergence. Then we have to look at what's going on at -1. This is just an alternating one. 1 minus 1 plus 1 minus 1 plus, and so on. This also diverges. The limit of the terms does not exist. So the limit of the terms is not equal to 0. The power series diverges at x equals -1. Note that we would not say that the series diverges at x equals 1. I might have said that. That was incorrect. The power series diverges at x equals 1. It only makes sense to say diverges at x equals 1 when you're talking about a power series. So this means that -1 is not in the interval of convergence. So our interval of convergence we can write in absolute value notation. Absolute value of x has to be less than 1. We could write it in interval notation. -1 to 1, not including -1, not including 1. We can write just a regular inequality. X is strictly less than 1 and strictly greater than -1. This third one here is the most shorthanded one. We could draw a picture of our interval of convergence. -1 is not included. The center is at 0. 1 is not included, and I want everything else. So here we have an absolute value inequality. The second one is interval notation. This third one is just a compound inequality. And this last one is a graph. All ways to describe in the interval notation and in the graph, I use parentheses to indicate that an endpoint is not included. So an alternative is to use brackets facing outward. So this is another fairly common notation to say the endpoints are not included. Some were concerned, some people were concerned that -1, just in parentheses, if both endpoints are not included in the interval, people might interpret this as a point. But if someone said the interval of convergence is from -1 to 1 in parentheses and wrote it down this way, not said it, but wrote it down this way, They just said it's an interval of convergence and therefore it is not an ordered pair. But it's understandable. You want to use a different notation, so they write the brackets, but turn the brackets out. Like the brackets want to be are not including the endpoints by turning their back on the endpoints. Very Klingon this style. I'm pretty sure this is the way Klingon has of the endpoints based this combination. All right, so tomorrow we want to do the same kind of thing that we did yesterday. We want to look at a power series and write down what the interval of convergence is. Where's the center? What's the radius? Are the endpoints included? That's the three stages of looking at a power. And we want to do this rapid fire. We don't want to have to write down all these ratio tests. Look how long it took. I can't even fit it all on one page, mostly because I drew this extra graph. So if I kind of. We want to be able to go right to the answer. We don't want to have, the point of a math class is to not have to write down all the friggin' math all the friggin' time. We just want to be able to read what's going on. We want to know what's going to happen in the ratio test. We want to know what's going to happen in the ratio test. There should be no surprises. All right. Tomorrow we'll do more examples of the ratio test for finding the interval of convergence for a power series. That's going to do it for today. I'll see y'all on tomorrow. But have a good day and thanks for playing.